see some nods. So for here, we'll be covering how to find and load pandas on your local HPC resource, how to load data into data frames in whole or in part. That will mostly be review. Estimate the size of your data in memory, reduce your data size by converting to appropriate memory saving data types, run some standard functions with multi-threading using Numba, and then load and write out of memory files with chunking. For this, we recommend that you use Jupyter Lab unless otherwise advised, but it's ultimately up to you what kind of interface you want to use. I'm just going to I use Jupyter Lab because it has a very nice interface for viewing data frames. Just so you know, this course is mainly focused on the functions and workflows specific to using pandas on an HPC cluster. The basic functionality will be discussed only briefly. If you want a more in-depth introduction into the pandas library in general, I also offer I, as a representative of NAISS, also offer a different course, an introduction to pandas for data science, typically in the spring. So for those of you who are not familiar, Pandas is short for Panel Data Analysis. It's a Python data library for cleaning, organizing, statistically analyzing moderately large, up to about 3 gigabytes data sets. You can handle more than that as well. It just can get more difficult. It's originally developed for analyzing and modeling financial records, which are also called panel data over time. But it's since expanded into a package rivaling SciPy in both the number and complexity of available functions, and also kind of the resemblance of being a bit of a Franken package, and that the quargs and terminology and jargon can vary a bit from sort of the types, groups of modules to groups of modules, depending on the background of the people developing those different types of functions. So that's the main drawback of pandas, is that the nomenclature can be a bit inconsistent, but as far as functionality goes, it's great. Get automatic explicit data alignment, so you can access any cell, any subsection of the data by corresponding row and column labels, so you always know exactly which data you're selecting. You can do all sorts of manipulation on the data within and across data structures, remove, transform, broadcast, compare, all of that stuff. There are close to 30 different I/O interfaces for different file types, including Excel, JSON, HDF5, NetCDF, SQLite. There are several SQL formats alone. It has a simple interface with the Seaborn plotting library, which I'll be covering a little bit later this morning, and very easy multi-threading with Numba if that is installed on your system, or if you're able to install it in your own environments. Apart from the jargon being a little bit inconsistent, the one other drawback is that the parallelization support is somewhat limited, but you can build things like Dask or polars on top of or in parallel with pandas and get that functionality back. And if you have higher dimensional data than 2-dimensional data, it's sometimes recommended to use the X-array package instead. And that's because it expands pandas functions to higher dimensional data sets. But that's outside the scope of this workshop. So let's start with discussing how to load and run the data. Pandas is part of the SciPy bundle and has been since 2020. So at most HPC resources, you'll have to load a SciPy bundle. You'll need to use module spider SciPy bundle to see which versions are available and how to load them. Just so you know, Pandas requires Python 3.8 and newer. So if you're using SciPy bundles for Python 2.7, you're going to be disappointed if you're looking for Pandas. Some facilities also have Anaconda, which typically includes Pandas, JupyterLab, NumPy, SciPy, and pretty much all the other popular packages. But like I said, if there is a Python package that you want that is not included, you'll have to install it in your own environment because LMod modules don't. For Anaconda, they don't really stack like they do with pip installed Python modules. So at HPC2N, these are the combination of modules that you'll need to load. The reason Matplotlib and tk-enter are included are because a few of these, because a couple of the examples used Matplotlib to show the data. I think those examples were actually removed since the last time, but someone else added those back. Anyway, so these are the available SciPy bundle versions as of last year. The reason that there aren't any new versions this year is because for 2025 is because there have been some issues with the numerical stability for versions for 2025 versions of SciPy bundles. So they're not installed in very many places anywhere, and even if they are installed, they're not recommended. So for this workshop in HPC2N and for and LUNARC, we both use 2023.11. And for LUNARC, these are technically the only modules that you need. If you want to do some plotting, you also want to include Matplotlib or Seaborn or both. If you want to use Jupyter on Cosmos, Jupyter will load NumPy, SciPy, Matplotlib, Seaborn, and pretty much all the other packages automatically. So you don't actually need to load any modules. In fact, I will go ahead and open one just so you can see. So I will call up this JupyterLab CPU. And I want it to go for the rest of the morning. So I'm going to ask for 2 hours. Actually, no, I'll need to start it again with. No, I will start with 2 hours. And for later on, you're going to want a bit more than one task per node. So for one of the Numba demos, I asked for 4 tasks per node. So you go to this gear icon, you click it, and under tasks per node, you increase to 4. And that will tend to reset, but that's okay. And then pick the correct project number, click start. And if you have a separate Conda environment that you wanted to load. Oh shoot, you know what? I just realized I actually do need to load the separate Conda module or separate Conda environment because that's where Numba is installed. So I have it installed in my TensorFlow environment. And so now let me stop and restart. And now JupyterLab is open. All right, so let's go back to here for a little bit. So if you're on UPPMAX, or if you're on Pele, everything you need is inside this SciPy bundle 2024.05-GFBF-2024A. That includes NumPy, SciPy, Pandas, everything, except for Matplotlib, which you might want to load separately. And if you want to use Jupyter, then you want to follow the instructions that are given at this link. On Tetralith, these are the modules that you should load. Again, you need to load a build tool -easy build, then GCC, then Python, then SciPy bundle, then Jupyter Lab. And if you're on Dardal, unfortunately, Jupyter Lab is only available through ThinLink, and as there are only ThinLink licenses, you don't trust that you're going to be able to get that. And even if you do get that, the queuing times are typically prohibitively long. So I recommend that for this, you want to work on the exercises with a local installation on a personal computer, or if you absolutely have to use Dardal, just run the commands from not from the command line. There are running scripts that are available in the exercises on GitHub. So let's go to over here. So if you go to the GitHub repository, go to HPC Python exercises, and day 3, see the data files, and the programs are in here. And you'll also see some center specific folders, and each one of these includes the .sh files that you need to run the scripts at your respective institutions. So those are available if you want to skip ahead and go ahead and make sure that you're able to run your programs on your respective institutions. It's recommended that you at least try the exercises yourself first, but those are available as solutions if you just need to go ahead and get running. So for this, if you're on Dardal, you'll need to load Cray Python /3.11.7. That includes NumPy, SciPy, and Pandas, and those don't require any prerequisites. Again, if you want to actually view the data, then in graphical form, then you might need to load Matplotlib, and then that would require PDC old, and then Matplotlib 2023.12, and then Matplotlib, this Matplotlib module separately. If ThinLink is available, there are these instructions are available to attempt to use the available interactive development environments. But again, don't trust that these will be available. And lastly, Alvis. These were newly added. Again, you should use the Alvis portal. And then once you've asked for a desktop, compute in the left-hand menu, open a terminal, load the Jupyter bundle, and maybe the Matplotlib, if you want that, which will load SciPy bundle on the fly. You can also just load this. You can also use module load. You can also use ML Spider SciPy bundle to see which versions are available for those, and load that instead of Matplotlib if you don't feel like using, if you don't think you're going to be using any visualization. So if you want to know whether or not Pandas is right for your data, I recommend going through this little flow chart that I mocked up. The data are 1D or 2D. That's a good sign. If you think named or timestamp indices will help, well, yes, they will. They definitely will. If your data are 2D, and first evaluate whether they're image data or tabular. If the data are image-like, then you might prefer X-array. And also, if your data are n-dimensional or higher dimensional, then you might prefer X-array. If your data are tabular and they're less than 3 gigabytes in memory, then Pandas is pretty much all you need. If they're more than 3 gigabytes in memory, you might need to add DASC or polars, or else there are ways to load data in chunks that are more manageable, but that's but then you can use Pandas only. You can use Pandas by itself only if you don't require any coordination between those chunks. If you need to have all 3 gigabytes plus in memory at the same time, then you're going to need something like DASC or polars to handle it. Now, this Pandas section will be split over this segment and the next hour, or rather the next 45 to 50 minutes. So I'm hoping to get through to about, like to get to the efficient data types or NUMBA JIT compilation before the end of this section. So for some introductory topics as a review, the main object types are series and data frame. The data frames are essentially 2D arrays where every column is a series. And for each series, you have a 1D array of customizable indices attached to every entry for easy access. And for data frames, you also have column labels. So you can access every row and every column by label, or multiple subsets, or multiple columns and multiple indices at a time. Numerical data are typically stored as float or N64, but you can convert to 32, 16, or even 8-bit versions of either to save memory. The object data type stores any of string, bool, list, or tuple, or mixed data types. Malformed data are also often designated as object type, and often that's a clue if you have data that are, if you're processing other people's data and you see something that looks like it should be numeric, but it's object type, that's often a clue that something has gone wrong. For the rest of the lesson, by the way, if example data frames will be typically abbreviated DF in code snippets. And if I use a series, it'll be abbreviated SEER. Pandas also has a lot of different functions for time series. So there are some data types like date time, time delta, and period that are specific to date times. And there's also a special date time version of not a number, which is called not a time, or NAT. And that's why Pandas has special functions for detecting non-numeric values, which are like .is in A or .not in A. And that's because there was the not a time data type necessitated a special NAND detection function specific to Pandas. There are also a few specialized data types that I'll go over in some more detail a little bit later. And I bring these up because these are good for saving on memory or performing window operations or other functions that you typically can only perform on an HPC cluster. So there's categorical, which is sort of a set-like data type for non-numeric data with very few unique values. the unique values are stored in the attribute categories, and then the actual location of the data in the data frame in memory, instead of having a whole bunch of different copies of the same sort of non-numeric value, it has like a little bit switch. That's a bit code that is associated with each category. So it's very, very efficient. You can have data savings, or you can have memory savings of like one or more orders of magnitude with categorical data sets just within a particular series. There's also an interval data type, and that's used for like windowing operations, and these can be sort of, if they're done using like a Q-cut or a cut operation, which is where you can sort of reclass numerical data into sort of ranged bins, and then those occupy memory in a way that's similar to the categorical data type. And so that gives you some extra memory savings as well. It's a discretizing function. It's output by discretizing functions, in other words. And then there's the sparse data type. And that's a data type based on the SciPy sparse matrices, where the omitted value can be a nan, it can be 0 or -1 or whatever other fill value you choose. And this placeholder value is stored in the data type instead of in the actual location of the array in memory. And then the rest of the data frame is compressed. So it only stores it doesn't store anything at the coordinates of the missing values. This is far from an exhaustive list of data types that are unique to Pandas, but these are the most important for HPC operations where you need every little bit of memory that you can get. Now, for loading and creating data frames, these are the most popular options, but like I said, there's probably about 30 of them in total. And you can find the full table by clicking this link here. So you can see there's quite a lot of options here. So these are the most popular. These are just the most popular, and I picked these out because a lot of these are, several of these also offer chunking. And for most of the text readers above, you can also load data. Ooh, that didn't work out right. For most of the text readers above and the Excel reader, you have quargs that let you choose to load only some of the data, like in rows and use calls. So that allows you to load only what you need and save some more memory. Use calls is pretty much the same as in NumPy's load text and gen from text functions. So it selects the columns by position index and returns the data structure containing only those columns of data. And in rows lets you read only the first in rows with their column headers. You can also select in rows equals 0 if all you want is just the column labels. And that's a very efficient way to inspect, just to preview what you have. And I already noted that those were picked out because they allow chunking. In most reader functions, also there's including this index call equals 0, also allows you to set the first column as the row labels. And that's real nice if you have something like like the exoplanets data frame that I included in the data sets. And that lets you access each exoplanet by name, as opposed to the arbitrary indexing that's applied if you don't supply this quarg. If you don't supply this quarg, the first row in the data frame will be assigned index 0, the second one will be 1, and so on and so forth. And it's completely arbitrary, and you can, and often not particularly useful. So typically you want to include this index call equals 0 if you want to access data by name. Or by date, by time index, by label, whatever. You typically want that. All right, so for the first exercise, I'll pause here for a couple of minutes. So what I want you to do is open your preferred IDE and load the provided exoplanets underscore 5250 underscore Earth units underscore fixed .csv into data frame, preferably with index call equals 0. And then I want you to save it to a text file with a tab separator. So get to where you've opened Jupyter or whatever other index you want. And you can code along with me if you would like. I should say fixed. So just, you can set df equals read CSV. Since this is in the same directory as my file, I will just do fixed.csv. Index call equals 0. And then just so you can see what that looks like, I will print df.head. And that prints this .head inspection function is that's a way to view the first 5 rows of the file. You can also specify a different number, like 3. Oh, right. I got ahead of myself there. So import pandas as PD dot read CSV. There we go. So this is what you should get. I also highly recommend making use of this info inspection function. By the way, that you might find another data set that does not have this fixed. If you don't, or if you load the one that does not have fixed, you might see that mass and radius are object type. And that's because there were, the original file had a couple of missing values specified as spaces instead of just leaving them without anything and having them load as nans. So spaces are always interpreted as intentional, even if they're in numeric columns, and they will turn numeric columns non-numeric. And the reason for that is that, again, initially this was for financial data. So some of the numeric columns might have been things like zip codes, where in Sweden, some of our zip codes have spaces in them. So white spaces are assumed to be intentional, and they can mess with your data. So that's why if you're doing anything else with this file later, like for exploring with plots and things like that, you want to use the fixed one. And now if you want to write this to file, you would just put df.to CSV, to CSV. And I'm just going to title this the same thing, but .text. And then to get the tab separation, you need tab sep equals \tab. And typically and if I run that, then if I go to teaching where I oh, sorry, this is in Pandas exercises. And if I look at what this output, then you can see this is the same data frame that we already loaded, except now instead of commas, everything is separated by a tab character. And the reason this wasn't used the first time is because these have spaces in them, but you can set the separator character to be specifically tabs. I'll close both of those. All right, let's get back to the exercises, or not there. So this is the solution you might have already looked at. Did anyone have any issues getting this to work, or getting Jupyter Lab to work, or anything like that? I'll take the silence as a no. Building data frames in series from scratch is also is just as easy. You can convert lists and arrays directly to series and data frames just by plugging them into like pd.dataframe or pd.series. And they also have an index quag to assign a list of numbers, names, tables, or other hashable keys to each rows. And there's also a columns quag for the data frame function to assign the list of names to the columns of the table. The equivalent for pd.series is just the name quag, which typically you don't bother to set this unless you intend to add that series to a data frame later. You can also convert dictionaries and record arrays to data frames, and can also convert data frames and series and all of that stuff back to NumPy arrays or record arrays. So very quickly in your preferred IDE, I'd also like you to instantiate a data frame with 4 rows and 3 columns. Label the 4 rows W, X, Y, Z, and the columns A, B, C. The contents of the cells are up to you. What I did was use just a data frame reshape. So I'll just call it df2. And code along with me if you want. Data frame. Then I'm going to import NumPy as NP. And then I'm going to call NumPy.arange 1 through 13 dot reshape 4,3. And then I'm going to set let me remind myself, is it index or index calls? Yeah, index. Set index and then copy these. And for columns, I'm going to title it this. And then just print df2 just so you can see what it looks like. And there we go. So very, very simple and straightforward. All right. So there's a solution. For inspection and data usage, or for inspection and memory usage, first, let's go over, I've already shown you head, or df.head, which prints the first 5 rows. There's also df tail, which prints the last 5 rows. And both of these print those 5 rows with both their row and column labels, so you can see how they're formatted and what the columns are labeled. And also you can plug in a different number in as an argument to either of those functions to print a different number of rows. There's also DF info, which I also showed you, which shows you, let's go back up here and take another look at it. DF.info. So you can see the info on how many entries there are total. It gives you the first and last index, so you can see what those are. Gives you the column index, the column name, how many values are not NaN, and the data type of each column. Then it summarizes the data types that are available, and then it gives this memory usage estimate. Now, this memory usage estimate it's the sum of the memory usage of each column, but only exactly where the full data frame appears in memory. If there are object type data, then those columns are storing pointers to other locations, and those are not necessarily factored into that memory usage. So what you're getting is the memory usage of the pointers to objects, not the memory usage of the objects themselves. So that's why there's also this df.memory usage function. And that returns the estimated memory usage per column, but it's most useful if you also set this quar deep equals true. By default, deep equals false, and that returns the values that, like I said, are what are summed up in the memory usage reported by df.info. And that's not typically what you want if you have values that are not numeric. With deep equals true, the sizes of strings and other non-numeric data are factored in, giving a much better estimate of the total size in memory. So I believe I have you. No, I do not. So what I'm going to do now is print memory usage. I'm going to print memory usage, the default version. And as you can see here, it's reporting that everything has a memory size of, I believe that's 42,000 bytes a piece. However, if I print deep equals true, now what you see is that the index, the planet type, and the detection method, because these are all string values, these have now ballooned in size to almost 10 times the size. Almost 10 times 10 times the size initially reported. So that's something to keep in mind. Operations. So I'm not going to go through these in detail because these are extremely extensive. The full documentation is extremely extensive. And most of these are more about the basic usage of Pandas and not HPC specific usage. But I will touch on the fact that these exist. So, and that a lot of these functions are vectorized specifically to avoid iteration through loops, which is costly and usually avoidable. And by costly, I mean it uses a lot of memory and a lot of time. So for string operations, you have this .string .method or .string, and then you have method where the methods are basically all of the built-in string methods. Those basically broadcast that function. The string accessor basically broadcasts that built-in function to all of to the entire column. For statistical functions, like all the NumPy statistical functions or ufuncs, and a few of the SciPy mstats functions, as well as a couple of cumulative functions that are available only through Pandas can also be called to be activated on whichever function you're applying it to, or whichever column or columns you're applying it to, automatically for the entire column. And you can also change the axis so you can apply it over a row, aggregate over a row instead, for instance. And the reason I show these is because these functions, all of these functions can be accelerated with Numba as well, at least by having them operate on multiple columns in parallel. So that's where you can get a lot of speed up. For binary and comparative methods, the standard operators work when both data structures are identically shaped or when one is a scalar. But when you have one data frame, when you have a series acting on a data frame, then you need special Pandas versions of those operators. Like you have an add, a sub, a mul, a div, and then reverse order versions of the same. And these you call off of the data frame. So like df dot sub, and then the name of the series that you're subtracting from each column. Things like that. There's some, and then there are 4 different ways to apply user-defined functions. There's a map function, which takes scalar functions and broadcasts it to element-wise to every element of the data structure. There's ag, which applies one or more broadcasting or aggregating functions like mean or standard deviation to a series data frame or to different groups in a group by object. And you can apply, you can use it to apply multiple aggregating functions at the same time, or different aggregating functions per column for multiple columns. Similarly, with transform, you can broadcast function to every cell of a data frame, series, or group by object that calls it. But group-wise functions, transformations can yield surprising results due to how group by objects are received. So these can be tricky, and sometimes you need to use apply instead in order to be able to apply custom functions to group by objects. Apply can handle expanding functions in addition to the aggregating or broadcasting functions. But by expanding functions, I mean you have like a list output for each individual input cell. Its flexibility and relatively intuitive interface do come at the cost of speed, so the output structure can be a little bit unpredictable when the inputs are grouped by objects, which I do not have time to go into in this lecture, unfortunately. And pipe is useful when you need to chain a whole bunch of different functions that take and return whole data frames or group by objects. Anyway, I highly recommend that you read all of the subsections of the documentation under function application if you want to know, and read the examples if you want to know how these functions actually work. If you're not familiar with how these work already. I want to get through at least one of these HPC specific topics before we go to our first break. So we already discussed one of these efficient data types, the categorical data. So the categorical data type maps all the unique values of a column to short numerical codes in the column's place in memory, and then stores the code in the smallest integer format that will fit, or that will fit the largest value code. So like if you have a data frame with 50,000 columns, but one of those columns has only or 50,000 rows, but one of those columns has only like 30 unique values, then you can store that column as a categorical data type, and then it will have codes numbered like 0 through 29. And that means each code will only need to be stored with a 2-bit integer. And that can save a lot over even like a 64-bit integer. This data type is extremely efficient when the number of unique values are small relative to the size of the data set, but it's not recommended when half or more of the data values are unique. If you already have an existing data frame, you can you can select the column and set it equal to itself, and with .as type category attached to the end. And if you're defining a new series that you want to be categorical, you can include this D type equals category. So as an exercise that you can code along with me, I'm going to convert the planet type column of this data frame to categorical type and show you exactly how much memory we're going to be saving. So I'm going to df, and you can please feel free to code along with me. Planet type. So this planet type column only has 5 unique values. So if I do, and this modifies the original data frame. So you're not creating a copy. You're modifying the original data frame by doing this. As type, category. And then I'm going to print this again and show you the change. So you can see before I converted data type or the planet type column to as type category, it took up 300,000 bytes, and that dropped to 5,700 bytes after converting to category. So massive savings, like almost 2 orders of magnitude. How are we doing time-wise? Now, each individual, that's weird. Now, I should note that the memory, these are all memory estimates. So they're usually, even with deep equals true, it's still a memory, it's still an estimate. So it's not all, okay, I see what's happening here. What's happening is that the individual column, if you print the full data frame, what's happening is that index is still the planet type column here. All you're seeing is the values of the codes. The values of the memory usage of the planet type labels is itself also still stored somewhere else. But even when you do that, even factoring that in, where'd it go? The before version, before converting to categorical type, the planet type column took up about twice as much space as it does after. So you're still saving a lot. Numerical data can also be cast as categorical by using these pandas.cut or pandas.qcut functions. And then these bins effectively create group by objects under the hood, and they're automatically assumed to be in ascending order. One of the other things that you can do with categories is that you can assert orders with these and use those for sorting. Now, I should note that the Pandas data type categorical is named for the general data science term categorical variable, which is a classifier like species, sex, brand name, etc. The Pandas data type will always be typeset as code and capitalized in this documentation. But sometimes I will refer to other data as categorical data types when I'm referring to the general term. And in that, you'll see the categorical written out in regular type font. Given the time, I'm going to go ahead and recommend that we take a break. We are, whoops. What happened to the, okay. Yeah, given the time, I recommend we go ahead and take a break and resume at 11:15 with sparse data. So we'll be a little bit behind, but hopefully not too much behind. Any questions before I sign off? Yes, that's a no. So let's resume at 11:15. So we left off at finished up categorical variables and or the categorical data type, which is for saving space on categorical variables. There's another somewhat similar data type called sparse data, where if you have a data frame where half or more of the entries are nan or some filler value, particularly if they're like numeric, then you can use the sparse array format or sparse D type to save memory. So you can initialize series or data frames with as sparse D type by setting the core D type equals pd.sparse D type. And then it's because sparse D type is itself has a D type arg, you need to give it a D type like float 64 if you've got very large float data, or and then give it a fill value. If you give it a fill value of none, the assumed value is nan, so not a number. If you already have existing data, you can convert them by setting the data structure equal to itself with dot as type called off of it. On the right hand side, you have dot as type parentheses pd dot sparse D type, and then give it the data type and the fill value. The data of sparse D type data have a dot sparse accessor in much of the same way as the categorical data have a dot cat, and string data have dot string. Most NumPy universal functions will also work on sparse arrays as well. And these are a few of the attributes and methods that you can use. So you can change the fill value, you can compute the fraction of the data that are not nan, you can convert to the SciPy sparse Q type, which I personally have never used, but I'm sure some of you have. This little example below shows the difference in memory uses between 1,000 by 1,000 identity matrix as a regular NumPy array versus a sparse D-type data frame. So you can see that if you have a 1,000 by 1,000 identity matrix, that's 1 million entries. and each one of them is about 8 bits. So you get, or 8 bytes. So you get an 8 million byte array. But then if you store it as sparse D type, even if all of the numbers are float, and let's say the fill value is 0 because it's an identity array, then that reduces the memory footprint of this array by well over 2 orders of magnitude. So definitely worthwhile if you've got sparse arrays. All right, let's move on to some of the more, what I think are interesting things to do with all of these data types and functions once you know how to use them. If you have the numba module installed, you can easily set engine equals numba in most built-in functions, and then set engine quarks equals, and then curly braces, parallel, true, like it's a dictionary. And with these, with these argument or quarks in place, what this does is that it allows you to run whichever function that you've called in parallel over the columns. And what numba does is it uses just-in-time compilation to compile pure Python code into machine-optimized form at runtime. And that automatically incorporates multi-threading across however many available CPU cores you've made available. So the functions that this works for are statistical functions like mean, median, and standard deviation. This can be applied to the whole data set or to rolling windows. And this can also work on complex or user-defined functions if you give those functions a @JIT decorator before on the line above the def line when you're defining the function. And then you apply the function via .ag, .transform, .map, or .apply, and plug in these engine and engine quarks into these, or as quarks to these function applying, these function applicators. Keep in mind that this parallel function evaluation occurs column-wise, so the performance will be boosted only if the function is repeated many times over many columns. For very small data sets, the added overhead could actually worsen performance. So, but it doesn't actually take that many columns to improve performance if you have even a moderately large data frame. By moderate size, I mean like several thousand rows. And since JIT compiled functions are parallelized column-wise, you want to make sure that, you want to make sure that the number of threads allocated for any interactive session or SLRM script is less than or equal to the number of columns you want to process in parallel. Assuming you've imported numba as numba, the way to tell numba the number of threads to use is numba.setNumThreads, and then give the number of columns that you want to parallelize over. And what I have it as an example here is I've loaded this COVID-19 Italy region.csv file, which has records of the numbers of like cases, hospitalization rates, ICU rates, deaths, recoveries, tests performed, things like that. So I will actually split this so you can split this data frame here. So what I'm going to do is ef.info, just so you can see what I'm loading. So it's got about 6,000 rows. That's it's basically a time series over 21 regions of all of these different stats taken during the COVID pandemic over the course of the first, I think it's a little bit more than a year, but not by much. And so I can show you how this works so the number of non-numeric columns goes from here onwards. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. So you would think you would get the best performance by using 10 threads. And I did go back and change the requirements to set this to 10 threads. So let's see how that performs. Now, one thing I have observed with this is that sometimes if you run this same function multiple times, you'll get the amount of time given for the second time it will decrease if you run it multiple times. So it may be more accurate to, if you want the most accurate estimate, you probably want to like close this and then reopen it and start from scratch. But so I've gotten values ranging from about 300 to, I want to say, close to 800 microseconds, as opposed to 1 millisecond without number. So here I'm just calling the mean in a rolling window of 630, which is basically a 10-day window. That's a 10-day smooth window over the 21 regions. No, sorry, it's a 30-day rolling window. Now, I mean, technically this isn't really sensible because you really need to separate out the different regions in order to do this properly and divide them by their normalize them by their populations. But again, this is just a demo to show you what Numba can do. And if you're calling a user-defined function off of this, it's the engine quarg and the engine quargs are the same. Pedro? Yeah.
I think the longer time that is observed in the first case it is because Numba is doing some compilation, right? And
Yeah,
then
I mean,
in the
well,
second, yeah,
and it's partly that and partly the fact that Numba is running all of these functions over each column in parallel. And the reason that, so you might expect more time gains than from the parallelization than you actually get, but there is some overhead because Numba does compilation first. And that's why
yeah,
it
yeah.
can actually add to overhead if you have a very small data frame or a very small number of columns.
Mhm.
Okay. So that was Numba. There is an alternative to JIT, and that is Cython. I'm not going to go into this in detail because the typical usage requires you to write a .pyx file with and compile it with a .setup.py file, and that requires the .pyx file requires a little bit more C experience. But if you're working in Jupyter, there's very minimal additional code if you want to use Cython. I will refer, but I leave it as an exercise to the reader to follow these links and take a look at how this works. The examples that are shown here with Cython use the magic operators, which are these percent signs and then these or the double percent in Cython before the actual function. So one other thing you might be interested in doing if you're about to run on HPC on an HPC cluster is to get dummy variables for machine learning. This is extremely easy. All you have to do is call this pd.getDummies, give it whichever data columns you want to convert from categorical data type to dummy variables, and then you can set things like dtype equals bool. These are the default settings. One of the arguments that you do want to pay attention to, though, is this drop first. This is one that you do want to use if all of your columns are, if all the categories are mutually exclusive and non-membership in the remaining categories is necessarily perfectly correlated with membership in the drop category. If there is some sort of secret unincluded other column, then you don't want to do that. You don't want to drop first. As for dtype, the bool setting uses less memory, but you can also use float or int for which might be necessary for certain modules. I think TensorFlow and PyTorch both accept this bool version. You can also set prefix as a set of strings that you can add to the dummy column names to make clear which ones are related. For data, this is the entire data frame. The way where you set columns is here in this columns quark. That's the one where you specify the quarks to convert to dummy variables. If you don't pass anything to columns, Pandas will try to convert the entire data frame to dummy variables, which is usually a bad idea, especially if there are numeric columns. But anyway, so here's an example function where I show how this is being used. So I've imported random choices just to mock up the data. This is let's say you did an experiment where you surveyed 10,000 people to see if their preference for Coke or Pepsi correlated with whether the container it was served in was made of aluminum, plastic, or glass, and whether it was served with or without ice. So I'm giving it a random sample of Coke and Pepsi. Containers of choices, or containers are the choices aluminum, glass, and plastic. Ices, this is a Boolean variable, so I don't have to convert that. Then I create the data frame, and to create the dummy variable, all I've done is plug in get dummies, plug in the variable, set drop first equals true. Given the columns brand and container material, because with ice is already Boolean. And then I'm giving it and I've given the prefix was and in. Just so it sort of makes grammatical sense. So the initial data frame has data that kind of looks like this: brand, container material, ice, with ice. And then the dummy variable version of the entire data frame looks like this. So the with ice column is moved up to the front because I didn't bother converting it. Was Pepsi is now a Boolean. Basically, this means, was it Pepsi? If it's not Pepsi, it has to be Coke. And then there's in glass and in plastic. And if it's not any of these, that means it was in aluminum. And now if I look at the memory usage of these data frames, the first one and the second one are quite different. So brand is almost 7 times large. Brand and container material are both almost 7 times larger as the original categorical variables as they are as these dummy variables. So not as memory efficient as the categorical data type, but the advantage of this is that you can use you can still use all of the NumPy ufuncs on these, whereas categorical data type does reduce the amount of the number of functions that you are allowed to use on the variables. All right, one last thing before we jump over to Seaborn. So the one thing that if you have a data set that is out of memory or larger than memory, then your first instinct should be to load only the columns and rows that you need. But if that's not enough, then several of the most common Pandas data reader functions like read CSV have a chunk size quark that allows you to read in and work on out of memory data sets in batches. The chunk size, whether that's rows or the number of bytes, depends on the data type that's being read in. So for CSV or Excel or things like that, the chunk size is the number of rows. For an Apache Parquet file, then chunk size might be an actual size in memory, which it will sort of basically it won't exactly it won't like truncate rows, so you don't have to worry about that, but you won't necessarily be able to dictate the number of rows that come out. Similarly, the common writer functions also let you append chunks to file rather than overwriting them. And that lets you write files that are larger than memory. And that requires the quark mode to be set to A for append. Be aware that you have to set up the chunk iteration such that header is false, or header is true for the first chunk and false for all the others. Otherwise, it'll try to inject header rows before every single chunk, and that can be a problem. I don't know why they haven't set it up to fix that issue yet, but that's still an issue as far as I know. Or at least it was in the versions that I tested. So while loaded, chunks can be indexed and manipulated like full-size data frames. And the workflows that can be applied to chunks can also be used to aggregate over multiple files. So it might also be worth breaking a single out-of-memory file into logical subsections that individually fit into memory. And then you might only have to do chunking once just to write those files. The Pandas documentation on chunking actually chooses this method of demonstration rather than showing how to iterate over chunks from an individual file, which wasn't the most practical demonstration, maybe, but since iterating chunks over an individual file is the slightly harder version, but to be fair, most data sets that are now publicly available are split into manageable file sizes, and it's spread over multiple files. So this Pandas documentation on chunking is probably more appropriate to data that you'll find in publicly available data sets. Now, those types of data sets tend to be curated, and the data that you produce will probably be less curated because it'll be more raw and not necessarily meant for public viewing. So the following example and the later exercise use this table, Global Disaster Response 2018 to 2024.csv. It's not out of memory for a typical HPC cluster. And actually, I don't think it's even out of memory for a personal laptop. but it's large enough that the additional overhead of chunking does not significantly change the computation time. It's a matter of seconds anyway. So contains 50,000 rows of data that are kind of in arbitrary order. I couldn't find any order based on the headings of the date, the country, disaster type, cost, response time, or any of the other columns. So that makes it kind of handy for for the exercise, which is this sort of makeshift bootstrapping that I'm going to show as a demonstration. So what I've done is, so I import pandas. I set include head equals true, and this is a switch that I'm going to toggle off after the first chunk. Then for chunk in pd.readcsv file name, I'm just giving it a chunk size of 10,000 to start because I know 10,000 fits in memory. And that means there's only 5 chunks. And for this, I'm sort of pretending to do some bootstrapping. This isn't really proper bootstrapping because the chunking ensures that you can't actually resample across you can't authentically resample across the entire data frame, but it's close. So each individual sample has a slightly higher chance of being picked because of the chunking than it would have if I had bootstrapped across the entire sample. But that's a statistics concern, not for us. So here I'm doing chunk.sample. This handy little function lets you sample some fraction of your data, or if you have a fraction value that is more than 1, then you have to set this replace equals true. And that means you're basically resampling the same data sets. This means you're resampling the same data set 5 times. And then I'm outputting this chunk to this CSV, Bootstrap Disaster Response 2018 to 2024 CSV. Then I set mode equals A, index equals false, header equals include head. And for the first loop, include head is true, so it includes the header. But by the second chunk, the include header has been toggled to false. So then that writes out a total of, so because this is, so then this means that each chunk individually is the same size as the initial data frame as a whole. So since I've already written this out, I have should have this somewhere in here. Might have been on my other computer. But anyway, this little example is a demo that where did the exercise prompt go? Okay. This is a little bit embarrassing, but the documentation, there was an example here in Pandas that was, or there was a prompt, an exercise prompt. Okay. Please cut that. So what I'm going to do as so here's what I'm going to do to demonstrate this. Another possible use. So one thing that you can do, since the chunking is, so chunking in Pandas works best when there's no coordination between chunks, but the operation, ideally you want to handle operations that handle each row independently. But some aggregate statistics can also be calculated if care is taken to make sure that either all the chunks are of identical size or that different size chunks are reweighted appropriately. If your data have natural groupings where the group membership is not known by position a priori, or where each group is itself larger than memory, you might be better off using Dask or other libraries. Also, keep in mind that windowed operations do not work on chunks because there's no overlap between the chunks. So there was supposed to be a prompt here, but I'll treat this as an example. So another thing you can use this for is I'm showing how to use this as for cumulative sums, which do not require coordination between the chunks. So here I'm just accumulating a sum of the total amount of money that was spent on all of these disasters. And I'm doing it chunk-wise. So I've initialized the sum to 0, and then I'm just sort of racking it up over each chunk. All right. So here are the key points on Pandas. It lets you construct list or table-like data structures with mixed data types, the contents of which can be indexed by arbitrary row and column labels. We talked briefly about what series and data frames are. How there are hundreds of methods and attributes that can be called on Pandas structures to do all sorts of cleaning, inspecting, organization, function application, all those other kinds of functions. Categorical and sparse data types can help you reduce the memory footprint of your data, as can using the dummies, the get dummies function, although the get dummies function is mainly for producing Boolean or integer columns for input into machine learning programs like TensorFlow or PyTorch. Most Pandas functions that you can apply most Pandas methods that apply a function can be sped up with multi-threading using Numba, if they're applied over multiple columns and if the data frame is large enough for the overhead to make sense. You just have to set engine equals Numba and engine quarks, curly braces, parallel, true. And there's also there's also the fact that several Pandas reader and writer functions support chunking, which is loading subsets of data files that would otherwise not fit in memory. Any questions before we switch over to the last little bit on Seaborn?